Okay, so now we will start with palm calculus. So we have talked about palm probability in the past. Recall if we have any mark point process, then the distribution of the mark of any point is can be seen as a palm probability, because you need to first condition on the location of the point that there is a point there, and then you can talk about the mark of it. Without the point, there is no mark. So similarly, when we define the universal mark, which is mark which is a function of the whole point process, then we also talked about that what will be the property of this point process when we look from a point. So you have many points and you condition on location of one point, and the mark is the whole point process around as viewed from this point. Then we ask, how does this point process, the viewed point process, look like? Does it have this property? So when we condition on this location of the point and then we ask of any probability, then we call it the palm probability. And if there is no conditioning and if we just ask what is the distribution of the point process, that is the normal probability. We will see actually more interpretation of palm probability just to understand it better. So one is, how does the rest of PP looks like when you condition that there is a point at a particular location. So let P be a property of point process. Of course, P will belong to this N, because N is the set of all possible configuration of or all possible realization of point process. So when I say phi belongs to P, it means phi has the property P, or phi is one of the element of this set P, which is made from multiple configuration of the point process. So for example, you can think P as equal to phi has 2 points in a particular set P. So all realization which has 2 points in the particular set B will be in P. So if phi belongs to P, means phi is one of those realization which has 2 points in the particular set B, or this means that phi has 2 points in this particular set B, means phi has this property P. So now for a given PP, if we condition on a point at the origin for any realization, then probability that phi has a property P condition on the fact that phi has a point at the origin. This is known as the palm probability of this property P. So what will be the normal probability of this property P? It will be that phi has this property P. And the palm probability would be phi has this property P condition on that phi has a point at the origin. So which is given that phi has a point at the origin, the probability that phi has this property P. So that is the main difference between the palm probability of a property and the the normal probability of the property. So to denote this, we will use this particular notation P0P, where P is the property. First, P is the notation for probability, and the superscript O denotes that there is a point at the origin. So O is the origin. Okay, so just to be clear, phi P has a property P, condition that phi has a point at the origin. Probability of this is equal to P0P. Now normal probability, we just write P of P, which means probability of the property P. And in general, these two are not equal. So instead of conditioning on a point at the origin, we can condition on the location anywhere. So we can also say that phi has a point at x. Condition on that, what is the probability that phi has a property p, and to denote that we will use the same notation, only on the top there will be x. So you can put any location there and this will be equal to the probability of that. So if you recall, we'll take an example that P is a property that the point process has 2 points in the ball of radius r at center A. So basically you can look at this location. The point is located here and there is a ball at location A with radius r. So if the point process, conditioned point process, has 2 points in this ball, then we will say the phi satisfies this probability. And if we average over all realization and compute the fraction of how many point processes belongs to this ball, have 2 points in this ball, then we can compute the probability. And just remember, when we conditioning means we are only going to take those point processes which has a point at the origin. So out of those only we will compute the fraction to compute this probability. So this is a general thing that when we condition on a point, the distribution of the rest of the points may change. We remember this thing that conditional probability is different than the unconditional probability for in the general case. So therefore that is the main reason that if you do not condition on the origin, the probability that there are 2 points in this ball may be different than when you condition the point. And that is because the location of a point can affect the distribution at different of other points at different locations for a general point process. So this is saying same thing, only the conditioning has been removed to a point at x. So if you look at this, the point is at x, you condition on this point, and then you ask what is the probability that there is 2 points in the ball located at location A with radius r. And you can see even this probability locate condition at x or probability condition at 0 may be different. Now let's take a special case that point process is a stationary point process. And our goal is to create a condition between conditioning on x and conditioning on 0 at origin. So we have this, a property P says that we are interested in computing the palm probability, condition on the probability that per point at location x, the probability that phi belongs to P. And we say that this is equal to palm probability of P2 where conditioning is on the point origin. And we want to find out what will be this P2 such that we can say this thing. Right. Of course, P and P2 would be different because conditioning on a point x is different and conditioning on a point origin is different. To maintain the same probability, we have to make sure the event occurs with the same probability. And it's a stationary point process, so absolute location does not matter. Somehow, if we can maintain the distance between this conditioning probability and the point process, part of the point process in which we are looking at the property, then we can maintain this property. So look at this particular case. Suppose this one is, the first one is you have a point at x and then you are looking at the distribution that the probability that there are 2 points in this ball of a comma r. Right. Now if we shift this point process, shift the origin to x. So x will be the new origin, and now if we condition on a point at this location, then you can guess that all the points which were here will come to this, because we are only shifting the origin. So when you shift the origin from this to this, this will look like this, and all the points or all the happenings in this area will happen now here. So we can say that there are 2 points in this ball, then there will be 2 points in this ball. Remember, we are only shifting the origin. So this means probability that there are 2 points in the ball of A are conditioned on the location, condition on a point at x is equal to probability that there are 2 points in this ball conditioned on a point at the origin. And we of course assume stationarity, otherwise this will not be true. So what is this null property? That there are 2 points in this ball and that ball is located at a minus x location with radius r. Or you can see this is also the shifted version of ball AR when it's shifted by location minus x. So my new property P2 would be that the point process shifted by x has 2 points in the ball of AR, which is equal to point process has 2 points in the ball of a minus x comma r. Okay, so this is just a way that you can create some relation between shift the uh, conditioning on a point at origin or conditioning on a point of x for stationary processes. For if non-stationary process, when you shift, the distribution changes, so it's very difficult to compute this kind of things. So just to remember again, what is a conditional probability? It is, or you can also compute the expectation with respect to this probability method. So conditioning event B, we assume that it has a non-zero probability of occurring, and then condition that this event has occurred, we compute the probability of happening of A, which we denote by probability of A condition B, and is equal to probability of A union B, which means A and B both has occurred. What is the probability of that? Divided by the probability of B. So you can see in both this and this term, B has occurred. In the top, A has also occurred. So you are computing the probability that what is the chance that A and B both has occurred, and dividing it with the probability of only B is occurring. So this is a ratio of the probability that out of all the events where B has occurred, what is the probability that A will also occur. Okay, so that's why we call it conditioning, because B has occurred, and out of all those outcomes where B has occurred, what is the fraction of outcomes where A has also occurred? So it's a relative probability. So P of A is the probability that A has occurred, while the P A condition B is a probability that only out of the events where B has also occurred, what is the chance that A will occur. So let's take a small example. Suppose x and v are independent random variables, and I have to compute probability that y is less than half, condition that x is between half and 1. So I can apply the same formula. So this is my A and this is my B. So the probability of A condition B would be equal to probability of A intersection B. A intersection B means y is less than half and x is between half and 1. So what is that area where y is half and x is between half and 1, this will be y is less than half and x is, this will be this area. So I need to compute the probability of this area will be the numerator, and the denominator would be probability of b. Probability of b means x is between half and 1, and this is probability x is between half and 1 is this whole area. This will be my denominator, right? So you have to basically see the relative probability. If I only look in this blue area, which is denoting the denominator or denoting the b, if I look in only that area, what is the chance that the y is also less than half or a occurs? So you can basically see if this is the uniform area, then half is the probability, relative probability. So actually, if you look at this area, overall this has a 1 by 4 probability of happening, but relatively of this blue area, this has a half probability of happening. So this we can see also, this will be the blue circle area, and this is the blue rectangular area, and the probability you can compute because we know the distribution of x and y. So the top one, because of independence, this will be equal to probability that y is less than half and probability that multiplied by probability that x is between half and 1. Both are 1 half and half, and the denominator is also half. So the probability will be equal to half. Okay, so again to notice this point, probability that y is less than half is half condition relative when the x is between half and 1. And if you just compute the probability that y is less than half, then this will be this region, unconditional probability. And unconditional probability will also be half because they both are independent, so conditioning does not affect. But if they were not independent, then you will see both values will be different. So in short, conditioning probability represents the relative measure of subsets of B with respect to the measure of B. Okay. So you take the measure of B, which is now B has occurred. So B is the complete sample space. And then out of these sets, we create small subsets, which denotes A intersection B, and we compute the probability of this. So for the case of palm probability also, we condition that phi has a point at the origin and phi has a property P. So it means the conditioning event has occurred. It means we are only considering the point processes realization where P has a point at the origin. And out of those realization, we are looking at whether they have a property P or not, and what is the probability that they have this property. Now, PP with a diffuse mean measure or the intensity measure, you know the conditioning event that there is a point at the specific location is a zero probability. We have talked about this. For a diffused intensity measure, the point process has probability that the point process has a point at a specific location is a zero probability event. Right? And one example is the PPP with the diffuse mean measure. The event that phi has a point at the origin or any location has a zero probability. So how do we condition on this point? It makes it a little bit difficult. So let's take the same example, but now with the conditioning event we are taking is it's a zero probability event. So we are taking the A same, but the B is now probability that x is equal to half. So if x is a uniform random variable between 0 to 1, what is the probability that x is half? It is 0. probability that x is any value, it is a 0 because it's a continuous random variable. Right? Even in this area, if we look at what is the event that x is half, it is this line. And what is the probability of this line? It is 0 because line in a two-dimensional space has a 0 measure. So if I have to compute probability that y is less than half, condition on probability that x is half, you will say that now again I will compute the same thing. A is this, B is this. So I will compute probability of A intersection B. And what is A intersection B? It is the event that y is less than half and x is half. Right? So if you look at this is the event which is A intersection B, because here x is half and y is less than half. And what is B? B is the whole line. So I have to compute the relative measure of this black line with respect to this red line. Now the red line has a 0 measure and the black line also has a 0 measure. So the relative measure is 0 by 0, which is not different. But intuitively, if you ask from this figure, you can think that this black line is of the half length of the red line, so the relative probability should be half. Okay, so how do we formalize this argument? The problem is coming because the condition B event itself have a 0 measure. So all the subsets of this will also have a 0 measure. So the ratio would be 0 by 0. To understand this, how we can think, see the 2D measure, this probability measure is the area, right? The original probability measure between x and y is the area, and that is why the line has the 0 area, that's why it has a 0 measure. Now from the line, if I want to divide the area of black line to area of red line, we will come to the 0 by 0. But if we divide by the length of the line, then we get half. But the question is, the original probability measure is in the area. How can I take the length of the line instead of the area of the line? So we will first try to define this in the limiting sense, and then we will try to make an argument out of it. So what I do is I take a small event B epsilon, which is event that x is between half and half plus epsilon. So instead of saying x is equal to half, I am saying x is between half and half plus epsilon. So this is a small rectangle. Right? This complete red rectangle is denotes this event x. Now out of this x, you want to compute the probability that y, condition on this probability y is less than half. So the event A intersection B would be this shaded area, and the B would be the whole rectangle shaded plus this white part. So the probability of B would be the area of this big rectangle, which is equal to length 1 into epsilon. And this shaded area would be length is half into epsilon. So the ratio would be half epsilon divided by epsilon. This would be equal to 1. Right. So if I take B as a conditioning event, as a limiting event which has some epsilon, then I can divide the two areas. One is epsilon and one is half epsilon. As you take epsilon goes to 0, you can take the limit to be half. Although in the limiting case, both area would become 0 because epsilon goes to 0. So this kind of tells that you can take the limiting case and represent the length as the measure, because on the Other way, both are epsilon. On the width, they both are epsilon. Only the length matters when you compute these ratios. Okay, this just says the same thing. So the point to notice here is B is a line and B intersection A is also a line, because line is 1D, probability measure of B and all its subset is 0. Right? But B is still uncountable. It's a line. It's a very small set of the whole two-dimensional rectangle. It is so small that its measure is 0, but it is still uncountable. And when B has occurred, then B is the complete sample space. So probability of B should be equal to 1 in the relative case. So you try to redefine your probability measure such that occurring of B should have a probability 1. Right? And that can be done if you move from area to the line, because B is now a line, and to say that the line has probability measure 1, it means we have to talk about the as a length. Okay, because of uniformity I am keeping length. If you are not there is no uniformity, then you would go to another measure, but still would be a one-dimensional measure. So we have to move from a two-dimensional measure to a one-dimensional measure. So I'm going to define a new probability measure G, which we call probability condition on B. And if I put B here, then G of B is equal to probability of P condition B. And that should be equal to 1, right? Condition that B has occurred, what is the probability of B occurring is 1. So I have to define a new measure such that the probability of B should be 1, right? It means the probability measure of this line should be 1. And because of uniformity, it will only become just the length of the line. Okay, and the relatively, you can say the GA is just the length of line representing A, line segment representing A. Okay. And we have to make sure the relative measure of subset of this event is consistent with the original probability measure, because that was uniform. That is why we have also taken it a uniform measure. If they were non-independent or the original point process was not uniform, then you could take a different 1D measure, which can be computed similarly using the length, using the limiting argument. So same thing can be applied to the palm probability also. Remember, when we condition that phi has a point at origin, you are taking a zero probability event. You are only taking those realization which has phi has a point at the origin, which is very small. It has zero probability, but they can still be uncountable. They can be still uncountable number of realization which has a 0 point at the origin. So now you will look at only this set, redefine your probability measure in a consistent way that this is the sample space, and condition on this you will look at now how many realization out of this set has a property P. Okay, so in short, out of all realizations satisfying event B, we are interested in realization that satisfy property P and their relative size with respect to B. So we have learned about palm probability. The method involving palm probability is known as collectively palm calculus. So there are various derivation we will do which will involve palm probability. and overall the math behind it is known as palm calculus. So the question is, why do we need palm calculus? So let us see one application of it where you would see where we apply and how do we do palm calculus. So how do we compute a distribution of distance of the nearest neighbor? So suppose there is a point process, you have different points. You pick one point randomly, which is located at xi. Let us denote the distance of the nearest point from this point xi as di. So you find the nearest point. So this would be nearest point of this, and the distance would be di. So the question would be, what will be the distribution of di? So here, if you look at this point xi, and you look at other point, this is the closest point because there is no other point in this ball. So this will be your di. So what is the distribution of di? For that, you can just compute the CDF or CCDF of it. And in particular, we are interested in knowing what is the probability that di is more than some value r. So if point process is stationary, then the location of the point does not matter. You can take the point anywhere and the distribution would be same. So let us take the point at the origin. In that case, I can formally write this probability that di more than r is that the point is at the origin. See, whenever you talk about the nearest neighbor, you have to, this is the nearest neighbor of a point. So you have to condition on a point. Otherwise, the nearest neighbor of the point is not defined. So that if you take at the point at the origin, then this will be conditioned on the point that there is a point at the origin, and then the distance of the closest point of phi, right, from the origin, right, because there is a point at the origin, and excluding the point at the origin, right. When I look at the closest point, I am looking at the neighbor, so I don't include the point at the origin in this list, because if you include it, that will be the closest one from itself. That will be distance will be 0. So when you look at the closest neighbor, you're looking at all other points, right? And then you want to know that the nearest distance of the closest point of phi, right, from origin, excluding the point at the origin, is more than r, right? And then you are conditioning on the point at the origin. So this we can also write as probability that if you construct a ball of 0 comma r, right, there is only one point, right? Why there is a one point? Because you already conditioned that there is a point at the origin. So if you construct any ball which contains origin, there would be a one point in any case because of the condition. You just want to make sure that there is no other point in this ball, right? So the number of points in the ball of 0r is 1. Or you can also write this in terms of the reduced palm measure, where it will, we can say that probability that condition on a point at the origin, there is no point in this ball of origin other than the point itself, right? So remember this notation exclamation mark is the reduced palm measure, which means when you, whatever you say about phi, you do not, you condition on a point at the origin, but you do not include the point in the statement or in the calculation. So here they are both same things. First one says the number of points in the ball at the origin with radius r is 1, condition on a point at the origin. Second one says that condition on the point at the origin, the number of other points in the ball of 0 comma r is 0. So how do we compute that? Okay, and then if the point process is non-stationary, the distribution would change according to the point location. So here we have to talk about, take the point at a particular location. So let's assume the point is at x. In this case, the nearest neighbor distance of the point is denoted as dx, because this will be a function of x. And then I would say the probability that dx is more than r is probability condition that there is a point at x, distance of the closest point from x excluding the point at x is greater than r. So you can see that both this nearest neighbor distribution, I have represented them in terms of the palm probability. So to compute this, you will require palm probability, or basically you would require palm calculus, knowledge of palm calculus. And the computation of palm probability now is very specific to the point process. If you change point process, the method, the procedure to calculate it may change, and the value definitely will change. So we will now see two methods to calculate the same, one for percent point process, another from the binomial point process. And there is not exactly one method which works for all. You have to see the point process, and see its characteristics, and then we have to see how can you calculate a particular palm probability. So to calculate for the point process, I will apply method one, which is local approach. In that case, I will basically look at the local neighborhood of the palm probability, right? So you want to compute that there is a point, there is the ball of 0, r has only one point, condition on a point at the origin. So I will construct a small neighborhood around this point. Okay, and this is basically beneficial for Poisson point process because we have this area independence property on the point property also, the point independent property also. So when we ask what is the nearest point from point at the origin, we'll look only in the area where it is local to the point at the origin. Okay, and in that case, so basically I want to ask condition that there is a point at the origin, the probability that B0 has one point, and this is what is also equal to the nearest neighbor distance, which we are interested in. So how do we go about it? We will basically consider a ball around the origin of radius epsilon. Okay. So I will construct a small ball around the origin of epsilon radius, and I want to compute that there is a point in this ball of 0, r, right? And I want to condition that there is a point at the origin, but instead of basically considering the point at the origin, I would consider that there is a point in this ball of 0, epsilon. Okay, and if I take epsilon goes to 0, this small ball will just become very small around the origin. So as epsilon goes to 0, the conditioning on this has one point is same as conditioning that the origin has one point, right? And this is to avoid that zero probability conditioning on zero probability event. Right? Conditioning on a point at the origin is a zero probability event. It may be difficult. So what I do is I take a limit approach. I considered a ball of 0, epsilon, condition that there is a point at in this, and then I'll just take epsilon goes to 0. So this conditioning event will be equivalent to conditioning on a point at the origin. Okay, so what I want to compute is probability that ball 0, r has only one point at phi, condition origin has a point in phi, and I want to say that in the limiting case, when epsilon goes to 0, this is equal to probability that the ring ball 0, r minus ball 0, epsilon has no point, given ball 0 epsilon has one point. Okay, so this is the probability that the ring has no point in it. Okay, so conditioning on ball 0 epsilon has one point. I can either say the ball 0 r has only one point, or I can say the ring has no point, right? Because there is only one point in this ball, and if I include that area, the rest of the ring area should not have any point. Otherwise, the total number of points in this ball will be more than one. So this is probability, this conditioning one, A conditioning B is probability A intersection B divided by probability of B. So this will be probability the ring has no point and the ball 0, epsilon has one point divided by the probability ball of 0, epsilon has one point. Right. Now if you look at this and this are condition independent event because the ring and the ball of 0, epsilon are exclusive sets. So we have learned that the Poisson has this area independence property. So if there are two disjoint sets and you talk about what is happening in those sets, the probability would be independent. So this will be equal to probability that ring has no points multiplied by probability that ball 0, epsilon has one point. The numerator and denominator will cancel. So this will be just equal to the probability that ring has no point. Okay. So, and now what is the probability that ring has no point? This will be the void probability of the ring, right? And it's because of the Poisson, it will be given as e to power minus lambda into area of the ring. So area of the ring is pi r square minus epsilon square. So this will be epsilon is e to power minus lambda pi r square minus epsilon square. Okay. Now only thing is remaining is you to have to take epsilon goes to 0, right? So that you get the palm probability condition on there is a point at specifically at origin. So once you take epsilon goes to 0, this will just become e to power minus lambda pi r square. So probability that ball 0 comma r has only 1.5, condition on origin has 1 point is this, right? Or in other word, you can say the ball 0 has no other point. Okay. And we see that even if you don't condition and just ask probability that ball 0 comma r has no point, that is also equal to the same, right? So this is just reassurance of Slavnak theorem, that conditioning on a event, conditioning on a point, and then you look at the neighborhood without that point, that probability will not change. It will be just as the unconditional probability of the same event. So the probability that the ball 0 comma r doesn't have any point is also equal to same, in particular to same as probability that ball 0 comma has no other point, condition that there is a point at the origin. Okay, so in this case, conditioning on the point at the origin, distribution around it does not change for PPP. Now let us take another example where I am going to take the binomial point process. And here I'm going to take a global approach here because local approach may not work here. So you know that binomial point process is an area in W and it has endpoints, and it always have endpoints. And it's suppose we take the uniform binomial point process. So any point probability that it is in the area dx is dx by area of W. So probability that here we want to compute the same thing, conditioning on the point at the origin. What is the probability that the ball of 0 comma r has 1 point? Okay, so condition that there is 1 point at the origin, the probability that ball 0 comma has 1 point. And how do I compute this? So remember, the binomial point process does not have area independence property, right? But it has one property, that there are always endpoints. Okay, so if origin has 1 point and you want to compute that ball 0 comma r has 1 point, this means other than the origin there should not be any point in this ball, right? So this complete ball has only 1 point. Okay, so this will be same as the outside of this ball has n minus 1 point, right? So saying that a particular set has 1 point is same as saying that the outside of the set has n minus 1 point, because they are the same event. In the binomial point process, if A has k points, then the A complement will have n minus k points, right? This will is because the total summation is always n. So computing the probability that the ball 0 comma r has 1 point is same as computing the probability that outside of the ball, which is W minus ball 0 comma r has n minus 1 points. Okay, so what I want to compute is probability that W minus ball of 0 comma r has n minus 1 point, condition on origin has 1 point, right? Now these are the rest other n minus 1 point, right? So now what we can say that the conditioning event, I'm talking about a particular point that it is at the origin, and in the numerator I have a event which depends on the rest of the n minus 1 points, right? And we have point independence in binomial point process. So whatever is happening to the first point does not affect where the rest of the points will fall, right? So probability that the rest n minus 1 point falls in any set, that is independent of whatever is happening from the first point, right? So this conditioning that origin has the first point is at the origin does not affect the distribution of the rest point. So from the independence of these points, what you get is this will be equal to probability that W minus ball 0 comma R has n minus 1 points. Okay. Now you have to only compute this probability that this particular set has n minus 1 points, right? So from the binomial point process, I know that in any area A, the point will be placed with A by W probability. So here in this case, A is equal to W minus ball 0 comma R. So n minus 1 points will be placed in A with probability. They are all independent. So if one point is placed with P probability, n point will be placed with P to power n probability. So here we have n minus 1 and individual probability is A by W. So what we get is A by W to power n minus 1. Okay, and A in particular is W minus B 0 comma R. So volume of A would be volume of W minus volume of ball 0 comma R. Okay, so if I put that volume of A, which is volume of W minus volume of ball 0 comma R, which is pi R square. So what I get is this A by W is 1 minus pi R square by area of W. Okay, and then you have n minus 1. Okay, so the probability the near that then there is no other point or the nearest neighbor is more than r distance away is given by this value. Okay, and if you look at the unconditional probability that the ball 0 comma has no point, that is given by that there's all the points are outside this ball, so that will be given by a by w to power n. So these two are not same. So in binomial point process, the probability that the point has the ball 0 comma r has no point is not equal to probability that the ball 0 comma r has no other point, condition that there is a point at the origin. So conditioning on a point at the origin does affect the distribution of other sets. Okay. So we discussed two methods to compute this palm probability. Okay, now that was first interpretation. Now we go to the second interpretation of palm probability, which is known as, so first one was that it is a conditional probability. Palm probability is basically that you condition on a point and then you ask what is happening to its neighborhood or rest of the point process. In this new interpretation, where we saw talk about the view from a typical point, right? So instead of conditioning on a point, we just pick a random point. Okay, and we go to that point and ask whether the view has a particular property. So consider a property P, select an arbitrary point or a typical point in the point process, which is selected without any bias. So let's suppose this point is xi, and then let us ask a question. What is the chance that the view from this typical point has the property P, right? And what is the view from a point means? You go to the point, make that point origin, and then you look at the point process, right? So this just means that you shift the point process by minus xi, right? When you shift the point process by minus xi, the point at the xi becomes 0. That becomes origin. Okay, the whole point process shifts to that. And then you say that this new object, phi minus xi, shifted version of phi, has a property P. Okay, and the xi is selected, it's a typical point, so you can choose any point. So this just means the prompt probability of P would mean that a view from a typical point should have that property P. And what is the probability that the point would have that property? So let us, so this is a question we are interested in. What is the probability that the view from a typical point has the property? Okay. So for that, what you can do is let's assign the following mark to each point. You go to xi and you shift the point process back and ask whether this new shifted version has the property P. If it has, the mark will be 1, otherwise it will be 0. And the mark distribution, if you compute of this point, probability, what is the probability of mi equal to 1? And if it's a stationary point process, all the marks would have the same distribution. Then you would just say that probability that mi equal to 1 is that you go to you condition that there is a point at xi, right? And then you go to that point, shift the origin there, and then ask whether the shifted version has the property p or not, right? Because that is the mark distribution, right? The mark distribution mi is 1 when the shifted version to a typical point would be would have the property p. To get that, you have to condition that there's a point at xi and then compute that. So right, as a stationary process, then what? Yeah, shift the origin to a typical point, and you can see the point as a new origin in the shifted version, right? And when a stationary process, then you don't have to condition on an arbitrary point. You can just assume that the point is at the origin itself, because absolute location of the points does not affect the distribution. So instead, I can just say that the probability that there is a point at the origin, phi has this property. Okay, so that's how both interpretation and matching in the stationary cases, when you have only when the location does not matter, and the non-stationary cases also the interpretation matters, because then is also interpretation are same, because then you have to just condition on a point at location x. Okay, so basically a illustration for that is, suppose you have this point process and you have a set b, and then you want to compute that property p, that there is no point in the circle of radius r around point a, right? So if there's a point at the origin, you want to make a ball around a with radius r and ask what is the probability that there is no point in this ball. And if you look at the palm probability, so you can condition on a point at phi, and then you can look at uh, this probability that this ball does not have this point, right? And this in the stationary process, you have taken it origin, right? Or you can take origin can be somewhere else, and you can just pick one point, and from that point make that new origin, and then the whole point process will be now phi minus xi, and then you ask in the new shifted version, does this new point process has a point in the ball of a comma r? Okay. So the mark distribution will be probability condition on a point at xi, whether the shifted version has this property p, the view has this property p, and the stationary case, you can just assume that conditioning is on a point at the origin, and just ask conditioning on a point at the origin, what is the probability that the point process has this property. Okay. The third interpretation would be, instead of actually going to one point, you can also compute the average over all points to get the average mark distribution. Okay, and that will also give you the same palm probability. So we can go to each point xi, look at the pp from that point, and the point pp that the point c around itself is phi minus xi. For this shifted version, there is a point at the origin, right? And then we ask the point, do the pp you see has the property p? And then average fraction of points that would say yes is noted, and that will give you the palm probability of that property, right? So instead of just picking one point, you can just go to every point and get an average. That is essentially the same thing. So uh, so question to the point, do the point process you see has the property p? You can mathematically represent the total number of points that say yes are the expected value of summation over all points xi, which are in phi. And then for each point, you ask whether phi minus xi has the property p or not, right? And you take the indicator. So if 5 of them say yes, you get 5, right, as a summation. So the fraction of point which say yes is given as this value divided by total number of points, right? So which will be summation of EXI, sorry, summation XI of the indicators, right? So for every point in phi, I add 1. So this will give you total number of points. Okay.
And suppose the point process is infinite, then the both denominator and numerator can be infinite. So to make it more tractable, what I do is I take a finite set B and I only ask all the points in that set B. And if it's a stationary process, this B does not matter, right? If you take a small b or a large B, or you take the B tending to cover the whole space, you should get the same thing, right? So since it's an infinite point process, we'll take a finite set B. Total number of points in set B which say yes are, you go to each point in phi intersection B, which means only points which are in B, and ask the question whether a shifted version has the property B or not. And when you divide by total number of points in the ball, you get the fraction, right? So what is the total number of points in the set B? That is just lambda into area of B, right? I'm assuming a stationary point process. So this is just lambda into side of B. Okay. So you can take any B for the stationary process, does not affect this process, the answer. And the numerator also, you can write this as equivalently summation over all points, indicator that xi belongs to B and indicator that phi minus xi belongs to B, right? So all the point where the xi is not in B, this will be 0. So this is essentially the same thing, whether you count over all points and multiply by this indicator, this will eventually remove all the points which are outside B, and you're only counting the points, uh, the indicator for the points inside B. Okay, so let's see an illustration for that. You have a point process inside B, and you want to compute the property that there is no point in the circle of radius R around point A. So what you do is you go to each point in the set B. So there are 3 points. First, to select this point, you make this new origin. So this is the new point process, and then you ask whether the ball of a comma r has 0 point. So here it is yes. Then you take the second point, make that the new origin, and then ask the same question. See, when you change the origin, the ball also shifts because ball is centered at a, right? So it has a distance from the origin. So when you change the origin, this ball also shifts. Here there is 1 point, and then you go to this point, and then you also see this. So there's no point in this. So 3 out of 3 points, 1 point say yes, right? So this will be 1 by 3, right? But in basically you have to average it over all realization of point process, or you have to take a very large b so that ergodicity can kicking in this, and then you can get the same answer from the single realization also. Right. So let us consider the following mark to each point. Mi is indicator that the view has property P. The mark distribution is given by probability Mi equal to 1. And in the stationary process case, this just means probability that condition on there is a point at the origin, the point process has the property P. Okay. And probability that Mi equal to 0 is just 1 minus that. Okay, so this neighbor image from a point is known as the universal mark, as all marks can be constructed from that, right? So if you consider this phi minus x as the view, as the mark itself in the extended notation case, then every mark you can think of can be constructed from this view, right? Dependent or independent. So if we now thin the, so what we said that the average fraction of point which say yes, right, which for which the mark is 1, right? So if I thin the point process such that I only retain the points which has mi equal to 1, right? So if I do that, I only get points which has mi equal to 1, and then you compute the intensity measure of that for set B. That way you also get the total number of points which is say yes, right? So if I thin the point process with this mark, retaining only points with mi equal to 1, the thinned point process suppose is known as phi dash, then the density of the new point process is lambda dash is equal to lambda into the probability of retaining, right? And what is the probability of retaining that? Probability that mi equal to 1, right? Because you are only retaining the point which has mi equal to 1. So retaining probability would be probability mi equal to 1, which is nothing but the palm probability that the P0 phi belongs to P. Okay, this will be my new density. Okay, so total number of points in set B for this new point process is equal to density into area. Density is lambda dash. So total number of points in the set is lambda dash into area of B, right? And if you compute the fraction, then basically you have to divide by the total number of points, right? So now if you look at lambda dash is nothing but I can write as lambda dash equal to lambda dash into b divided by b, right? So this b cancels. So lambda dash is equal to lambda dash b divided by b, right? And lambda dash b is nothing but the intensity measure of b, right? And what is the intensity measure of B? It is basically you go to each point and add all the points which are in phi dash, right? And what are the points which are that are in phi dash? Those for which the mark is 1, right? So basically it is same as saying that you go to each point in phi and then you look at the point in B and then you look at the point for which the mark is 1 and you count them. That is how you get the total number of points in the set B for the new point process. Okay, and the B is here, right? So now if I yeah, so this is what I get. Now also note that lambda dash is nothing but lambda into probability that m equal to 1, right? So from this, if you divide everything by lambda, what you get is probability, the Baum probability is lambda dash by lambda, which is equal to this by lambda b, right? Right. And now if you look at this is the average fraction of point which say yes, which is the third interpretation. So this just shows that the palm probability from the first interpretation that is same as the palm probability from the third interpretation, right? So you go to each point and count them that way, that will also give you the same answer.